Hi guys, here's a video going over your Chapter 2 test review. So hopefully it'll help you get prepared for your test, which is on Friday. So number 1, we have f of x equals 2x squared minus 4x plus 1, and part A says to express f of x in the standard form. So your first step is to factor out the 2, but only from the first two terms. So I'm going to write this as f of x equals, I'm going to factor out the 2, so that's 2x squared minus 2x, and then we're completing the square, so I'm going to go ahead and insert a box. I still have my plus 1 that's on the outside, and I'm going to subtract a box since I'm working on the same side of the equation, but don't forget, since I factored out the 2, that 2 also needs to go in front of the box. To figure out what number goes in the box, I'm going to take half of my middle term, which is negative 2, and then square it. So half of negative 2 is negative 1. Negative 1 squared is positive 1. So I have 1 and 1. And then from there, I can just factor and combine like terms. So I have 2, and then this quadratic factors to x minus 1 squared. And then 1 minus 2 is negative 1. So there's your equation in the standard form. Now standard form I also like to call vertex form because you can get the vertex just by looking at the equation. So your x-coordinate comes from the opposite of what's inside the parenthesis, and your y-coordinate comes from what's on the outside. So my vertex is at 1, negative 1. Number 2 is graphing a polynomial, so it says find all the values of x such that f of x equals 0. That just means you're finding the zeros and the end behavior, and then sketch the graph of f. So I'm going to start by factoring this. They all have an x in common, so I can take out the x. So that leaves me with x times x squared plus 2x minus 8. Your quadratic can be factored further. Two numbers that multiply to negative 8 and add to 2, that is that's positive 4 and negative 2. And then when it says find the values that f of x equals 0, that means I'm taking my polynomial and setting it equal to 0. So my first 0 is at 0, my second one is at negative 4, and my third one is at positive 2. So I'm going to go ahead and put those numbers on the line. So I have 0, negative 4, positive 2. I can go ahead and plot those 3 points. So there's my one at 0, my one at negative 4, and my other one at positive 2. For the end behavior, that's looking at the leading coefficient test. So my leading coefficient for this is 1. My degree is 3. So I have a positive leading coefficient with an odd degree. That means my ends are going in opposite directions. So as x approaches positive infinity, that means my function is approaching positive infinity. And since my degree is odd, my ends are going in opposite directions, so as x approaches negative infinity, f of x is going to approach negative infinity. That'll help you graph it, because at the 0 that's to the right, my function is going up, and the 0 that's to the left, my function is going down. And logically speaking, to connect all of these zeros, you would have to cross, but you can also look at the multiplicity of each 0. Each of those exponents were odd, like this one's 1, 1, and 1. So at all 3 of those zeros, it should cross the graph. So there's your graph of the polynomial. For 3 and 4, they're both division problems. Sometimes you can use long division, sometimes you can use synthetic division. It all depends on what you're dividing by. So for this one, I'm dividing by an x cubed, so that kind of forces us to do long division. So I'm going to go ahead and rewrite my polynomial. Don't forget that if you're ever missing a term, to put in a 0. So in this case, I'm missing the x squared. Minus 2x plus 7. And then on the inside, I have 3x to the 5th minus 4x cubed, so I'm missing my x to the fourth term. So put in a 0, minus 4x cubed. Missing my x squared term, so put in a 0, plus x plus 5. Now to actually go through the long division, I'm focusing on this first term. I'm asking myself what times x cubed gives me 3x to the fifth. That is going to be 3x squared. So I'm going to put 3x squared on top of my x squared term. Whatever number I put on top, I'm going to multiply every single one of these terms by 3x squared. So 3x squared times x cubed is 3x to the fifth, plus 3x squared times 0x squared is 0x to the fourth. 3x squared times negative 2x is negative 6x cubed. And 3x squared times 7 is positive 21x squared. Now with long division, you're always subtracting, so I'm going to draw my line and change my signs of all of the terms for that polynomial. This line's a little crooked, so I'm going to fix it. There we go. My first terms cancel. My x to the fourths also end up canceling because they were both zeros. That leaves me with 2x cubed minus 21x squared, and I'm going to go ahead and bring down the next term. So plus x. And then the process repeats itself, so what times x cubed gives me 2x cubed? That's 2. So plus 2. I'm going to multiply all four of these terms by 2. So that's 2x cubed plus 0x squared minus 4x, and then 2 times 7 is 14. Now if you'll notice above the 14 we don't really have a term, so I'm also going to bring down the 5. That way all of my terms line up. Still need to subtract, so I'm going to draw my line, change my signs. So my 2x cubes cancel. That leaves me with negative 21x squared plus 5x minus 9. Okay, so that is my remainder. So I'm going to rewrite my final answer. That was 3x squared plus 2 plus my remainder, which is negative 21x squared plus 5x minus 9 divided by what we divided by. So x cubed minus 2x plus 7. Now when you're dividing, the zeros are always optional when you're writing out the polynomial, but if you'll notice in the denominator right here, I didn't put my zeros in because I didn't want to rewrite everything. Alright, so that was long division. For number 4, I'm going to go ahead and do synthetic division since you're dividing by x plus a number. So anytime you're dividing by x plus a number or x minus a number, that you can do synthetic division with. Just remember that you're always using 0 for synthetic divisions, the zeros. So if my factor is x plus 2, then that means the 0 is negative 2, and that's what's going to go in the box. I can go ahead and list out my coefficients. So I have 6x to the fifth, I'm missing my x to the fourth, missing an x cubed, I have my x squared, missing my x, and then I have my constant. So this one you're missing a lot of terms. With synthetic division, your first term goes straight down, so I have 6. 6 times negative 2 is negative 12. I can combine, multiply, gives me 24. I can combine, multiply, that gives me negative 48. Combine, multiply again, combine, and multiply again. So my remainder is negative 200. So since my starting polynomial is x to the fifth, that means my answer is going to be 1 degree lower, so that's x to the fourth. So I have 6x to the fourth minus 12x cubed plus 24x squared minus 52x plus 104. And then finally my remainder, so plus negative 200 over what we divided by, which was x plus 2. You can also write that as minus 200 over x plus 2. Either of those answers would be fine. The remainder theorem uses synthetic division to evaluate functions. So I want you to evaluate the function at -2. That -2 is what goes in the synthetic division box. So the difference between the last problem and this one was I gave you it as a factor, so the factor was x plus 2. But for this one I want you to evaluate at -2, so we just leave that as the same sign. So you don't change the sign before you put it in the box. So I'm going to list out my coefficients, so -4, 3, -5, 7, -10. This one actually wasn't missing any terms, so we didn't have to put in any zeros. First term goes straight down, multiply, combine, multiply, I forgot to combine, and then multiply, so that gives you 54. Combine, multiply, and combine. Now it's called the remainder theorem because whatever your remainder is, that's your answer. So I have f of x, not f of x, f of -2, because that's what we were trying to find, equals -132. Now, for the remainder theorem, you do have to do the synthetic division, but if you wanted to check your answer, you could take -2 and just plug it in for x. But on your test, I'll be looking for the synthetic division, so don't just plug it in. Alright, to find a polynomial with the zeros of -7, 0, 4, and 3, you need to start by setting up your factors. So I have f of x equals, if I have a 0 at -7, that means my factor is x plus 7. If I have a 0 at 0, that means my factor is x. A 0 at 4 is x minus 4. And a 0 at 3 is x minus 3. I'm going to go ahead and rearrange this so that the x is in the front, because it bothers me when it's in the middle. And then from here, I'm going to go ahead and start to multiply. Okay, so I'm going to start by multiplying these two together first. So you can FOIL, use the box, whatever floats your boat. So that is x minus 7, or x squared minus 7x plus 12 once you actually multiply it. I'm also going to multiply these two together since that's just distribution. So that leaves me with x squared plus 7x. And then I can take those two quantities and multiply them out. So I have x squared times x squared is x to the 4th. X squared times -7x is -7x cubed. And just going through the distribution, plus 12x squared, plus 7x cubed, minus 49x squared, and then plus 84x. And finally, we can combine our like terms. So I have x to the 4th, my x cubes end up canceling out. Minus 37x squared plus 84x. And there you go. For 7, 8, 9, and 10, you're working with the imaginary and complex numbers. So 7, you're just adding, so that means we can just combine our like terms. So 5 plus 8 is 13. 3i plus -10i is -7i. So you have 13 minus 7i. And that's your answer for that one. Be careful with number 8. Make sure you rewrite it. So that's 3 plus 8i and 3 plus another 8i since it's being squared. And then you just have to run through the multiplication. So 3 times 3 is 9 plus 24i plus another 24i plus 64i squared. Don't forget that I squared is equal to -1, so that leaves me with 9 plus 48i minus 64, since I squared is -1. And then combine your like terms. So you get negative 55 plus 48i. For the two division problems, you're multiplying by the conjugate. So my denominator is 9 plus I, so I need to multiply by its conjugate, which is 9 minus I. And whatever I do to the bottom, I have to do to the top. And then from here, we just need to multiply. So I can distribute the 4 in the numerator. So that's 36 minus 4i. We talked about conjugate pairs and how the middle terms cancel out. So that leaves me with 81 minus I squared. Don't forget that I squared is negative 1. So I have 81 minus negative 1, which is actually 82. So I have 36 minus 4i over 82. All three of those are divisible by 2, so don't forget to reduce. So that leaves me with 18 minus 2i over 41. For number 10, you're doing the same thing. So my denominator is 2 plus 7i, so I'm going to multiply by 2 minus 7i, since that's the conjugate. Now this one's a little trickier because you do have multiple terms in that numerator, but it's just going through the process of multiplying. So I have 12 minus 42i minus 6i plus 21i squared in the top. And then the bottom, since they are conjugate pairs, your middle terms are going to cancel. So that leaves me with 4 minus 49i squared. Don't forget that I squared equals negative 1. So that's 12 minus 48i minus 21 on top over 4 plus 49. And then 12 minus 21 is 9, negative 9. So I have negative 9 minus 48i over 53. All right. Number 11, the possible rational zeros. That's when you're looking at the plus or minus p over q's. So plus or minus p over q. Usually the only mistake with this is people mixing up what p is and q is. So p is factors of your last, q's factors of your first. So I like to list them out first. So my factors of 8 are 8, 4, 2, and 1. And my factors of 3 are just 3 and 1. And then to get your final answer, listing all the possible rational zeros, you're dividing all of your p's by all of your q's. And each one gets its own plus or minus. Don't be lazy. Make sure you write the plus or minus there. Otherwise, it will take off like half a point. So put the plus or minus. So I have 8 over 3, and then plus or minus 8 over 1, plus or minus 4 over 3, plus or minus 4 over 1, plus or minus 2 over 3, plus or minus 2 over 1, and then plus or minus 1 over 3, and plus or minus 1 over 1. You do not have to state the same value multiple times, so if you end up reducing a fraction and you already wrote it down, you don't have to write it down again. For number 12, finding all of the zeros. So you need the calculator for this, and what you're going to do is you're going to graph the function and then use the calculator to find the 2 zeros that you actually see on the graph. And on the graph you should see a 0 at positive 2 and negative 0.5. To actually calculate the 0 at negative 0.5, you're going to hit second and then trace. So second trace, and it's option number 2, 0. And it's going to ask you for a left bound and the right bound. Your left bound is the tick mark that's directly to the left, so that would be negative 1. And then hit enter. Your right bound is going to be 0, and then hit enter. And ignore when the calculator says guess and hit enter again, and it should tell you that that 0 is at negative 0.5. So for this one you have two zeros because we're starting out with an x to the fourth and we need to break it down to a quadratic. So that means we have to do the synthetic division twice. So I'm going to start with my 0 at 2. I'm going to list out my coefficients. So that's 2, negative 3, 48, negative 75, and negative 50. And let's run through the synthetic division. And if you'll notice in the remainder box you do get a 0, which you should because 2 was a 0. So if you don't get a 0, you got to double check your work. And then we do the synthetic division again, but now we use the negative 0.5. So let's run through that. So 2 times negative 0.5 is negative 1. 50 times negative 0.5 is negative 25. And again, we get a 0 in the remainder box. So we did the synthetic division twice because we needed to get it down to an x squared. So now if I write out my quadratic, it's 2x squared plus 0x plus 50 equals 0. And we're trying to find the other two zeros, that's why we're setting it equal to 0. Now with this, you can use the quadratic formula if you want to. Your b is 0, but since I don't actually have a b, I'm just going to solve this equation as it is. So I'm going to subtract 50 from both sides, divide by 2, and then take the square root. So that leaves me with x equals the square root of 25 is 5, square root of negative 1 is I, and then whenever we take the square root, it's plus or minus. So your final answer is to just write all the zeros together. So we had the 2 from the calculator, that was 2 and negative 1/2. And now we have the other 2, and that was positive 5i as well as negative 5i. And my degree for this polynomial was 4, which means I should have 4 zeros in the end, which I now have. The 5i and the negative 5i you'll never see on the graph because your calculator will not graph imaginary zeros. It'll only graph the real ones. For 13, we're going backwards a little bit, so I'm giving you the zeros, and then you have to write out the polynomial. So don't forget that complex zeros always come in pairs, like the one on the last slide, we had positive 5i and negative 5i. So for this one, we have negative 2 minus I, so the 0 that goes with that is negative 2 plus I. So you need to physically write that down because I'm only going to give you one of them. And then from here, we set up our factors. So since I have a 0 at 2, my factor is x minus 2, because it's always x minus your 0. For your other two zeros, it looks a little weird because you're subtracting an expression. So it's x minus negative 2 minus I, and then x minus negative 2 plus I. I'm going to go ahead and distribute the minus in both of those parentheses because I don't like seeing the parentheses in the parentheses. I think it looks a little weird. And then I still have my x minus 2 in the front. I would highly recommend that you multiply those two first. That way you can get the i's out of the problem. You can distribute if you want to. I like using the box for this because it keeps my terms organized since you are multiplying 3 terms by 3 terms. I'm going to do that on the side over here. So I have x plus 2i, or x plus 2 plus I, and then x plus 2 minus I. And then I can just multiply the sides of my box together. So that's x squared, 2x, ix, 2x, 4, 2i, negative ix, negative 2i, and then negative I squared. So my ix's cancel, my negative 2i and positive 2i cancel, and then right here I have minus I squared, but don't forget that I squared is negative 1, so I really have minus negative 1, which becomes just a 1. And then I can combine my like terms. So now my polynomial is x squared plus 4x plus 5, because I have the 4 and the 1. And then that x squared plus 4x plus 5 was just coming from multiplying my complex zeros together. So I can write that. And I still need to multiply that by x minus 2. So that you can just do with regular distribution. So that's x cubed plus 4x squared plus 5x minus 2x squared minus 8x minus 10, and then combine your like terms. So I have f of x equals x cubed plus 2x squared minus 3x minus 10. And then that is your final polynomial. Alright, now moving on to rational functions. So number 14, does the function below have a horizontal or an oblique asymptote? Explain, and then find the asymptote. So anytime you're looking for horizontal asymptotes, you're always comparing the degree. So if you look at your numerator, my degree is a 2. And if you look at your denominator, my degree is a 1. And if your degree of the numerator, so that was this, if that is smaller than the degree of the denominator, then your horizontal asymptote is going to be y equals 0. It's not the case for this problem. If your degree of the numerator, again that's this one, is the same as the degree of your denominator, which again not the case, that's going to be y equals a over b. And then if your degree of the numerator is bigger than the degree of the denominator, you don't actually have a horizontal asymptote, you have an oblique asymptote. So does the function have a horizontal or an oblique asymptote? It has an oblique asymptote because the degree of the numerator is greater than the degree of the denominator. So that's your explanation. The degree of the numerator is greater than the degree of the denominator. To actually find the asymptote, you need to divide. So you can do synthetic division or long division for this one. This one I'm going to go ahead and do synthetic division since I'm dividing by x plus 3. So I'm going to put negative 3 and then my coefficients, so 1, 2, negative 8. Keep in mind, if this down here were like an x cubed or an x squared, you would have to do long division. But since it's not, might as well save the time. So that's 1, negative 3, negative 1, multiply, and your remainder ends up being negative 5. Now for your oblique asymptotes, we don't really care about the remainder, so you can kind of ignore this, and then just write out the equation that you have left over. So then that is going to be y equals x minus 1, or 1x minus 1, if you want the 1 there. Do not forget your y equals for your oblique asymptote. If you do, I will probably take off a point. So it's a line, so it needs to be written as an equation of a line. 15 and 16, we are actually graphing rational functions. So for number 15, I have f of x equals negative 3 over x minus 5. We're going to start by finding the x-intercepts. So your x-intercepts come from the numerator, and they're the zeros of the numerator. Now if you notice, without numerator you don't have an x up there, so that means you do not actually have an x-intercept. So none. Your vertical asymptotes come from the denominator, zeros of the denominator. So since my factor is x minus 5, my vertical asymptote is going to be at x equals 5. Your y-intercept comes from plugging in 0 for x. So if I plug in 0 for x, that leaves me with negative 3 over 0 minus 5, which is positive 3/5. And then your horizontal asymptote, let's compare the degree. So my degree on top is 0 because you don't actually have an x. And my degree on the bottom is 1, since that's your highest exponent. So my degree on top is smaller than the degree on the bottom. That means my horizontal asymptote is y equals 0. And this graph does not have any holes because you didn't have any factors that canceled out. Alright, so let's go ahead and start graphing. I'm going to graph my vertical asymptote at 5. I'm going to graph my y-intercept at 0 and 3/5. I'm going to graph my horizontal asymptote y equals 0. And that's all I really have to graph, and then you can use the graphing calculator to sketch the graph so you can see the shape. So just type it into your y equals and then hit graph, and the calculator should show you something like this. But on your test I will be looking for the asymptotes and any points that you plotted, and then you can just use the calculator to look at the shape. Alright, number 16, we can go ahead and start by factoring this. So that factors to x plus 3, x plus 1. We didn't have to factor for the last one, but this one we do. X squared minus 1, that factors to x plus 1 and x minus 1. If you'll notice, your x plus 1's cancel. So your leftover function is x plus 3 over x minus 1. Again, your x-intercepts come from the numerator. So zeros of the numerator, you have one at -3, so I'm going to have an x-intercept at -3. Your vertical asymptote comes from the denominator. So I'm going to have a vertical asymptote at x equals 1. Your y-intercept you get by plugging in 0 for x. You can plug into the original or you can plug into your leftover function. I'm going to go ahead and just plug into my leftover. But it really doesn't matter which one you plug into. So your y-intercept is at 0, -3. And then horizontal asymptote, let's go ahead and compare the degrees. So if you look at your original, and you can also look at your leftover function, but if you look at your original, my degree is 2 on top. My degree is also 2 on the bottom. So since my degrees are the same, your horizontal asymptote is going to be y equals a over b. A is the leading coefficient of the numerator. B is the leading coefficient of the denominator. So I have y equals 1 over 1. So just y equals 1. And then if you'll notice when we factored, we did have a factor that canceled. That's when you're going to have a hole. So my 0 for the factor that canceled was -1. So my x-coordinate for the hole is going to be -1. And then for my y-coordinate of the hole, I'm going to plug in -1 into the leftover function. So I have -1 plus 3 over -1 minus 1. That leaves me with 2 over -2, which is -1. Alright, let's go ahead and graph. I can plot my x-intercept at -3, 0. I can plot my y-intercept at 0, -3. I can plot my hole at -1, 1. So actually draw a hole, since it's not really part of your graph. I can graph both of my asymptotes. So I have one at x equals 1. And then I also have one at y equals 1. So there are your two asymptotes. And then I can use my handy-dandy calculator to look at the shape. But if you connect these three dots, you can kind of see the shape anyway. So heading towards both of the asymptotes. And then I have my other piece of the graph over here. But again, you can always graph it in the calculator to look at the shape. Alright, so that was graphing rational functions. The last thing we are doing is from section 2.7, and that's solving inequalities. So the first thing you need to do is get it equal to 0. So this one's already equal to 0, or you have the inequality equal to 0. And then from here we can factor it. So that's x minus 5 and x plus 3. And we want to see when that is less than or equal to 0. So to be able to do that, you find your critical values, or I like to call them critters. Your critical values are basically the zeros, so I'm going to have one at 5 and -3. So from here, I'm going to go ahead and create a number line. And put my 0 right there. 1, 2, 3, 4, 5, and 1, 2, 3, -3. And then this side is positive infinity, and that side is negative infinity. Now, since it can actually equal 0, that means around each of your critters, you're going to have brackets. So I'm going to have a bracket on this side and that side of -3. I'm also going to have brackets around that 5, and that's because your inequality can actually equal 0. And then to actually find your solutions, your intervals for your solutions, you're going to pick some test points and plug them into either the original function or your factored form. It really doesn't matter which one you plug into. So for example, my first interval, this one right here, goes from -infinity to -3. So you're picking any number between -infinity and -3. I'm going to go with -4, and I'm going to plug that into my function. So I have -4 minus 5 times -4 plus 3. I'm plugging it into the factored one. So when I choose -4, that gives me a positive 9. Now if you look back at your inequality, we want it to be less than or equal to 0. So is positive 9 less than or equal to 0? Of course not. 9 is greater than 0. So that means that interval is not part of your solution. So that's a sad face. And then I'm picking any value between my next interval, which is -3 to 5. I'm going to go ahead and pick 0. So I have 0 minus 5 times 0 plus 3. That gives me -15. -15 is less than or equal to 0, so that part of your intervals work. And then finally I need to pick a value from 5 to infinity, so I'm going to go with 6. So I have 6 minus 5 times 6 plus 3. That gives me positive 9, and I needed it to be negative because, again, looking back at your inequality, it had to be less than or equal to 0. So this interval doesn't actually work. So there's two things I'm going to be looking for. I'm going to be asking you to graph the solution. So the solution is going to be this part of your number line. So you just kind of shade it in. So there's the graph, and then you actually list out your solution, and the solution is the interval. So that interval goes from -3 to 5. So there's two things I'm looking for. I'm looking for your number line and the solution set as your intervals. For number 18, there's nothing to factor, so we don't have to factor it. So again, you're looking for your critters, your critical values. And your critical values for rational functions come from the zeros of the numerator and the denominator. So my 0 of the numerator, that's when 4x plus 5 equals 0. So that's x equals -5/4. So my first critter is at -5/4, which is also -1.25. And my second critter is from the denominator, and that's at -2. I'm using the decimal because it's easier to graph the decimal on a number line. So let's go ahead and create our number line. Put my 0 in the middle. So I have 1, 2, positive 2, 1, 2, -2. So this has to be greater than 0. It can't actually equal 0. So at each of my critical values, I'm going to use parentheses instead of brackets. So I have parentheses at -2, and then I also have parentheses at -1.25. So it's a little bit past -1. It's right there and right there. And then don't forget your infinities. So this side heads to positive infinity, and this side heads to negative infinity. So now you're picking values within all of your intervals. So you have your first interval from -infinity to -2. Your second interval goes from -2 to -1.25. And your third interval goes from -1.25 all the way to infinity. So you're picking any number that fits in those intervals. So for my first one, I'm going to go ahead and pick -3. So I have 4 times negative 3 on top plus 5 over negative 3 plus 2. And what I'm looking for is I'm looking for it to be greater than 0. So greater than 0 means it has to be positive. So greater than 0, and I got 7. 7 is greater than 0, so this part works. And then my next interval goes from negative 2 to negative 1.25. So I'm going to go with negative 1.5. So I have 4 times negative 1.5 plus 5 over negative 1.5 plus 2. And that gives me a negative 2, so that means this middle interval doesn't actually work. And then finally I'm picking a number from negative 1.25 to infinity. Let's go with 0. So I have 4 times 0 plus 5 and 0 plus 2. Gives me a positive 5 halves, and I was looking for a positive number because again it had to be greater than 0. So that means this interval actually works. So your graph, you just shade the intervals that work. So that's this part and this part. So I have my graph, and then the last part is to actually list out your solution as an interval. So I have 2 intervals. My first interval goes from negative infinity to negative 2. Don't forget the u because you have 2 intervals and that's the union. And my second interval went from negative 5/4 to infinity. You can use negative 1.25 if you want to, since that decimal terminates. But if you had a repeating decimal, I would much prefer the fraction. Alright, so there's your solution and your graph for number 18. And that is everything that you will see on your Chapter 2 test. Have fun studying!